Hello everybody, my name is Walid. I'd like to introduce one of the main statistic tests, which is the one-way analysis of variance, which is abbreviated by ANOVA. I'll talk about one of the ANOVA design, which is called the unbalanced design. Unbalanced design simply means that the sample sizes for the treatments or the groups are not the same. We know that the purpose of adopting the one-way analysis of variance ANOVA test is to check for the significant comparison between two or more than two means. First of all, let's understand this question. The data below are from an independent measure experiment comparing three different treatments. So we have three treatments. What is needed is to conduct a one-way ANOVA on the data to test the hypothesis, which states that the three treatments means are the same. Assume that all assumptions for the test are fulfilled. We talked about the assumptions in a previous video, and these assumptions states that the population for the treatments or the samples which drawn from these population should be normally distributed. The standard deviation for the population should be the same. For example, here we have three treatments or three groups. The standard deviation of the population which sample 1 drawn should be the same as the standard deviation for population 2 and same like the standard deviation for treatment 3. And we talked about the randomness and the independency between the three samples, which means that any sample drawn from its population shouldn't affect the data or the for the other treatments. And again, the last assumption is that we are dealing with only one independent factor. So as we see here in this table, we have treatment number 1 and the treatment number 2 and the treatment number 3. As we see here, the size of the sample for treatment number 1 is not the same as the sample size for treatment number 2 and not the same for treatment number 3. The question asks us to use the significant level to be 0.05. So this is a one-way ANOVA because we are dealing with one independent factor, and it is unbalanced design because the sample sizes for the three treatments or three samples are not the same. First of all, let's write the hypothesis to be tested. As we know, we have two hypotheses. The first one is called the null hypothesis, H0, which states that there is no significant difference between the three population means, or all the three means are the same. While the other hypothesis, which is the alternative hypothesis, states that at least one of the mean is different from other means. Maybe the three means are not the same, or maybe two means equal and the third one is not, same like what we have here. mu1 is not the same as mu2, but it is equal mu3, or mu1 is the same as mu2, but it is not the same as mu3. So we need to test the null hypothesis, which states that the significant difference between the mean does not exist. First of all, in order to make the calculation, we should calculate first the correction factor in order to calculate for the sum of squares. But first of all, we should make some calculation for the observation for the three treatments. For example, for treatment number 1, we have here the observation, and this is here the count for treatment 1. It is 10, while for treatment 2 it's 8, while for treatment number 3 it is 9. The summation of the observation for treatment 1 is 75. So we can simply calculate the mean for the treatment number 1. It is simply dividing 75 by 10, so we get 7.5. For the other treatments, the mean for treatment number 2 is 5.25, and for the third one it is 7.11. We need another calculation in order to calculate the correction factor. We need the summation of the observation, and we need to square this summation. So this is the summation squared for treatment number 1, and this is for treatment number 2, and this is treatment number 3. And also we need the summation of the squared of the observation. So this is the summation of the squared observations for treatment number 1, and this is for treatment number 2, and this is for treatment number 3. Now simply we can calculate for the correction factor. The formula for the correction factor is equal to the summation of all the observations. We square the summation of all the observation and divide by capital N. Capital N means the summation of the sample sizes for the three treatments. Summation of all X means summation of treatment number 1 and the treatment number 2 and the treatment number 3. Then we square this summation and we divide by capital N, which is simply the total of the sample sizes for the three treatments. Summation of X1 is 75. We can check from the table in the above, and for X2 it is 42, and for treatment number 3 it is 64. So we make the summation for these observation and square the summation of these, then we divide by capital N, or the total sample sizes. For sample 1 or treatment 1 we have 10 observations, for the second one we have 8, and for the third one we have 9 observations. Simple calculation, we get the value of the correction factor, and it is equal to 1213.37. We need this value, the correction factor, as I have said, in order to calculate for the sum of squares. Okay, now simply we can calculate the total sum squares, which is abbreviated by SS total. The total sum of squares. The formula for SS total is simply the summation of the squared of the observation for each treatment. This is for treatment number 1, and this is for treatment number 2, and this is for treatment number 3. And we subtract the correction factor from the total summation. So the summation of the squared for treatment number 1, it is simply 579, as we see here from the table. And for treatment number 2, it is 228. And for the third one, or third treatment, it is 468. And we subtract from these summations the correction factor we have just calculated. So simple calculation for SS total, we get the final value for SS total to be 61.63. So this is the value of the sum square total. It is 61.63. Now we need to calculate the sum of square between groups, which is abbreviated by SSB. The formula for calculating the sum of square between groups, which is SSB, the summation of the total observation for treatment number 1, we square it and divide it by the sample size for treatment number 1 plus the total observation for treatment number 2 squared divided by this sample size for treatment number 2 plus the total observations for treatment number 3 squared divided by the sample size for treatment number 3. All these summations we subtract the correction factor, which is already calculated. So direct substitution, we get the following: summation of x1 squared. This is the value for the summation of x1 squared, and this is the value of the summation of x2 squared, and this is for the third treatment. So for the first treatment, the summation squared is 5625, and the sample size for treatment number 1 is 10 plus this is the summation of the observation for treatment number 2 squared divided by 8, which is the sample size for treatment number 2 plus 4096, which is the total observation for treatment number 3 squared divided by the sample sizes for the treatment number 3, which is 9. All of these summation, we subtract the correction factor. So if you proceed, we get the following. These are the value, and the final calculation, we get the value of sum of squared between groups. So it is 24.74. So right now, we have calculated for two sum of square. First is the total, and the other one is between groups. So simply, we can calculate for the sum of square within groups. We know that the sum of square total is equal to the summation of the sum of square between groups plus the sum of square within groups. So we need to calculate for SSW. So simply we can move SSP to the other side, so its sign will be opposite, means it will be negative. So SSW will equal SS total minus SSP. Both of SS total and SSP have been calculated. So SS total is equal 61.63, and SS between groups It's calculated to be 24.74. So the sum of squares within groups is equal to 36.89. So all of the sum of squares needed to fill the ANOVA table have been calculated. This is the one-way analysis of variance table. And here we fill all the sum of squares for between groups and within group and the total. As we know regarding the one-way ANOVA table, the contents for this table are the source of variation, and we have two sources for the variation. The first one is between groups or between treatments, and the other one, it is within groups, which is considered the error. We need to calculate the amount of the degree of freedom. The sum of square have been calculated. Then we need to calculate the mean squares, MS. Then simply we can get the value of the statistic F. Regarding the critical value of F, we should return back to the F distribution table so we can determine it directly. Now let's talk about the degree of freedom. Degree of freedom. First, we need to calculate the degree of freedom between groups. Degree of freedom between groups, DFB. The formula for counting the degree of freedom between groups is very simple. It's equal to K minus 1. K means number of groups or number of treatments. And in our case, K is equal to 3. So directly, if we substitute for K3, we get the final value of the degree of freedom between. So it's 2. The next one is to calculate the degree of freedom within groups, which is the same as the degree of freedom for the error. The formula to get this amount is DFW is equal to capital N minus K. Capital N means the total observation for the 3 groups, and K means number of treatments or number of groups. So for sample or for treatment number 1, N1 is equal to 10, and for sample number 2 we have 8, and for the third one it's 9, so the total N is equal 27. And regarding the K, we have 3 groups, so the amount or the value of the degree of freedom within groups is equal to 24. So we calculate for the degree of freedom between groups and degree of freedom within groups. So simply to calculate the total degree of freedom, we make a summation for both. So degree of freedom total is equal to the degree of freedom between groups plus the degree of freedom within the groups. DFB is equal to, and DF within is equal to 24. So the summation is 26. So this is the total degrees of freedom. Now we can simply fill the amount we have just calculated for the degrees of freedom. We have 2 between groups, and we have 24 within groups, and this is the total degrees of freedom. Now let's calculate the values of the mean squares, which is abbreviated MS. So calculation of the mean square, it's very simple. First of all, let's calculate the mean square between groups, which is MSB. Simply the formula to calculate the mean square between groups is dividing the sum of squares between groups by the degree of freedom between groups, which simply means to divide this value, by the degree of freedom corresponding to. So if we substitute SS sum of square between, it is 24.74, and the degree of freedom is 2. So the final calculation for the mean square between groups, it's 12.37. So we calculate the value for MSB. Now we need to calculate the MS within groups, or sometimes it's called mean squares for the error. By the same technique, MSW, we divide the value of the sum of squares by the degree of freedom within groups. So SSW, it is 36.89, and the degree of freedom is 24. So the value of MS within groups, it's 1.54. Now we can fill these two values in the related cells in the one-way ANOVA table. So here we have the mean square between groups, and here we have the mean square for the error or within groups. Now we need to calculate the value of F-statistic, or sometimes it's called the calculated value of F. It's very easy. The formula states that the value of the statistic F is equal to the mean square between groups divided by the mean square within groups, which means simply dividing this value, which is the mean square between groups, by this value, which is the mean square within groups, or the mean square of the error. So after substitution, we get the value of the statistic F. So the value of the statistic F is equal 8.03. As the value of F-statistic becomes larger, so the probability of rejection, the null hypothesis, increase, which means as the value of the mean square becomes greater and the value of the mean square for the error becomes lesser, so the value of F becomes larger. So the chance for the rejection of the null hypothesis increases. So this is the value of the calculated F. It is 8.03. So this is the value of the calculated F. Now the rest, in order to complete all the contents of this table, is to determine the value of the F critical. And in order to determine this value, we should return back to the table for the F distribution. So what we have here is the F distribution table at alpha equal 0.05. In order to determine the value for the critical value of F, we need to know three numbers. The first one is the value of the significant level, which is already 0.05. And the second one is the degree of freedom between groups. And the third one is the degree of freedom within groups. So this table is related to the significant level, which is 0.05. Regarding the degrees of freedom, 2 and 24, this row here represent the value of the degree of freedom between groups. And we calculate the amount of the degree of freedom between groups to be 2, because we have 3 treatments. So 3 treatments minus 1 is equal to 2. The second degree of freedom is the degree of freedom within groups, or the degree of freedom for the error. It is 24. So for this column, this is the value 24. So the intersection for these two values of degree of freedom is 3.4028. This is the value of the critical F. So the value of critical F for significant level 0.05 and degree of freedom between groups in the numerator equal to, and the degree of freedom within groups, which is the denominator, is equal to 24. is equal to 3.4028. And if we round this digit to 2 decimal points, we get 3.40. So this is the way how to determine the value of the critical value of F. We use the F distribution table. Now we fill the last value needed to complete all the contents for the one-way ANOVA table. Now, in order to make a decision, we compare the two values. We compare the value of the F statistic, or the calculated value of F, with the critical value of F. And as we see here, the value of F statistic, or the calculated one, is bigger than the critical value of F. So in this case, we reject the null hypothesis, which states that the three means for the three treatments are the same. And because we reject this hypothesis, we accept the alternative hypothesis, which state that there is a significant difference between the three means. So this is the conclusion. This is the last conclusion. Because the value of F statistics, which is equal 8.03, is larger than the value of F critical, which is equal 3.40, we reject the null hypothesis. And the null hypothesis states that the three means are the same at 5% significant level, which means that because we reject the null hypothesis, we accept the alternative one. And the alternative hypothesis states that there is a significant difference between the three treatments, and mainly the three treatments means. In order to check for the significant difference between which means for the three means, we should adopt what's called the multiple comparison, or the post hoc test. So this is the conclusion which is needed for our question. So simply we compare the two values, the value of F calculated and the value of F critical. In our case, the value for the calculated F is bigger or larger than the critical one. So we reject H0. That's all for this video. Kindly, if you have any comments, please write it down. Thank you.